So let's dig deeper into this factoring quadratics concept. This is a big, broad concept, and we're going to break it into 3 different segments. Each of these segments becomes a choice that you'll have to make later on when you factor quadratics. So first of all, what is a quadratic? It's an expression where one or more of your variables has an exponent. Now, there are some exceptions, there's some additions, but for the most part and generally, that's what we're going to go with for right now. We're looking at expressions that have exponents. All right, we talked about factoring in the previous video. It's unmultiplying, so you're trying to figure out what 2 things were multiplied together to get these bigger things. The first thing you're going to do is determine what kind of a quadratic do you have. And there's only 3 options. You've either got a binomial, you've got a trinomial, or you've got one with 4 terms. So how do you make this first decision? Well, it's pretty simple. You count your terms. You're either going to have 2, 3, or 4. Now, how do you know what a term is? Well, they're separated by plus and minus signs. So let's just look. Here's some examples of binomials. You've got x squared minus y squared. You've got 8x cubed minus 27. Or you've got 5x squared minus 45. Here's some examples of trinomials. There are 3 terms for those. There's x squared minus 2x minus 35. That's a trinomial. There's 15x squared plus x minus 2. That's a trinomial. Here's an example of a 4-term polynomial. 6x to the 3rd plus 8x squared minus 3x minus 4. So for now, what you know about factoring quadratics is your first step is to take out a greatest common factor if there is one. If not, you're going to move on. First, you take it out. After you take it out, the part that is not the greatest common factor, that's what we're going to try to factor. So we're going to count those terms. Now you can count to 2, 3, or 4. So let's just say in the first place we count and we have 2. Let's look at the options you now have just for binomials. Let's say you've counted your terms and you have 2. So you have a binomial. Let's look at the options now. So you're still making choices. You're still analyzing. You counted your terms and you have 2. We look at those terms. You have to decide, do you have a difference of 2 squares, or do you have a sum or difference of 2 cubes, or neither one? First of all, you've got to know what are squares and what are cubes. Perfect squares are the numbers that you get when you square a number. If you square 3, and to the 2nd power means square. If you square 3, you get 9. Therefore, 9 is a perfect square, and 3 is the square root. All right, now, a sum or difference of 2 cubes. What are your perfect cubes? Well, one perfect cube is 8. You get that by taking 2 and cubing it. 2 times 2 is 4, times 2 is 8. So 8 is your perfect cube, and 2 is the root of that. You need to be familiar with your squares and your cubes, up to a certain point anyway, not 100 of them, but the first few. And if not, whenever you start factoring on a scratch sheet of paper, make a list of the perfect cubes and the perfect squares until you get really familiar with them. Now let's talk about your variables. How do you know that? Well, you know that x squared is a perfect square, and the square root of it is x. But what about your higher ones? Well, remember, when you multiply 2 bases together, you add the exponents. So let's just say I multiplied x squared times x squared. I get x to the 4th. That's an even exponent. Anytime you multiply a base with an exponent to itself, you know what? You're going to get an even exponent. If I do x to the 4th times x to the 4th, I get x to the 8th. Therefore, Anytime you have a variable that has an exponent that is even, you have a perfect square variable. And the square root of it is half of the exponent. For example, x to the 10th. That is a perfect square, and the square root of it is x to the 5th. X to the 18th is a perfect square, and the square root of that is x to the 9th. So even exponents are perfect squares, and their square root is half of that. Now, as far as a cube goes, naturally, x to the 3rd is a perfect cube, and its cube root is 3. Well, let's see what happens. You know, where do these other cubes come from? It can go higher than 3. What if I took x squared times x squared times x squared? 2 plus 2 is 4, plus 2 is 6. So there you go. What if I did x to the 3rd times x to the 3rd times x to the 3rd? You just cubed x to the 3rd. You multiplied it times itself 3 times. So 3 plus 3 is 6, plus 3 is 9. Do you see the pattern here as far as your exponents go? Perfect cubes are going to have exponents that are multiples of 3. So if it's a perfect square, your exponent is a multiple of 2, or an even number. If you have a perfect cube, your exponent is a multiple of 3. 3, 6, 9, 12, so forth and so on. Okay, so now that you can recognize them, let's check out what to do with them. Let's have a look at this one, and let's go through the steps one at a time. The first thing I know is I need to factor this quadratic. Well, I look for a greatest common factor, and there's not one, so I'm going on. I count my terms. 1, 2. All right, now that I have 2 terms, I know my only choices are as a difference of 2 squares or it's some difference of cubes. First, do you have a difference? Do you have a minus sign? Because if you don't have a minus sign between 2 perfect squares, you cannot use the difference of 2 squares formula. So I look at this one. I do have a perfect square, x squared. I do have a perfect square, 81. How do I know that's a perfect square? Well, I made a little chart down here of the first few perfect squares, and I see that 81 is a perfect square. Now here's your formula for the difference of 2 squares, and it says if you have x squared minus y squared, then that is equal to x plus y times x minus y. Now in a formula, when you have a variable to the 2nd power in one place, and then further on down you have that same variable without a power or to the power of 1, that represents the square root of this number. So in other words, this represents a perfect square, and this represents its square root. So to apply this formula, all I have to do is say the square root of this plus the square root of that times the square root of this minus the square root of that. If you notice, what you have here is a binomial times its conjugate. Do you remember conjugates? Where you have the same number but opposite signs? And if you FOIL this, if you use the FOIL method to multiply it back together, you're going to get this every time. That's how we got the formula. People kept on multiplying this, and they figured out, you know, every time I multiply 2 conjugates together, I get the first thing squared minus the second thing squared. Okay? So we're just saving time. All right, let's look at another one. Let's say x squared minus 36. What do you guess? What's your best guess? Well, do you have a difference of 2 squares? X minus 36 is 2 perfect squares, and it is a difference. So all you need are the square roots of each thing, x plus 6, x minus 6. And that is your answer. How about 2x squared minus, I don't know, 32. Well, let's go through the steps. Do you have a greatest common factor? This time you do. What's your greatest common factor between 2x squared and 32? So let's review this. The largest number that'll go into both of these things is 2. Now, when I divide that out, when I undistribute that 2, what do I have? X squared minus 16. So let's look at the leftover thing. Is that a difference of 2 squares? Well, x is a perfect square. I do have a minus sign, and 16 is also a perfect square. So let's just apply this formula. Now, when you apply the formula, you cannot lose this 2. So you're still going to have 2 times. All right, the square root of x is x minus 4, x plus 4. And it doesn't matter whether you put the minus first or the plus first, as long as you use one of each one. Okay, how about, real quick, x to the 4th minus 1. Do I have a greatest common factor? No. Do I have a difference? I do. Is this a perfect square? Yes, because the exponent is even. Is 1 a perfect square? It sure is. Its square root is 1 because 1 times 1 is 1. So let's factor this. The square root of x to the 4th is x to the 2nd. So I'm going to have x to the 2nd plus 1, x to the 2nd minus 1. Now, that is correct, but on this one, you're not finished. You're never finished factoring if it still fits any of these. So when I look at this second factor here, the x squared minus 1, I still have a difference of 2 squares. So I've got to factor it again. All right, this, the x squared plus 1, since it's a plus sign, you can't factor that. It's 2 perfect squares with a plus in the middle. You cannot factor that. So I'm going to leave it alone. This, I'm going to factor it again. The square root of the first term is x plus 1, x minus 1. And this is fully factored. If you went back in here and fold all this back together, you're going to get x to the 4th minus 1. Okay? So let's move on to sum and difference of cubes. First, let's look at these two formulas. If you will look at these, you'll see the formulas are exactly the same except for one thing, your signs. The sum of 2 cubes, x cubed plus y cubed, is equal to x plus y times x squared minus xy plus y squared, whereas a difference of 2 cubes is equal to x minus y times x squared plus xy plus y squared. We use a little trick here, the SOAP. That can help you remember your signs because your signs are going to be the same. That's the S. The next sign is going to be the opposite of that sign. And then the last sign is always positive. If you see that last sign, it's always a plus sign. So that'll help you memorize the formulas. But anyway, so let's look at this. First of all, and you go through these steps every single time. Do you have a greatest common factor? No, you don't. So let's move on. Count your terms. 1, 2. All right, I have a binomial, so I can either use the difference of 2 squares or the sum or difference of 2 cubes. Now, do I have a difference? Number 1, yeah. But do I have 2 perfect squares? No, I don't. So let's go on to cubes. Do I have 2 perfect cubes? Yes, I do. 8 is a perfect cube, x cubed is a perfect cube, and 27 is a perfect cube. 3 cubed is 27. How do I know that? Well, I've learned it. You're going to have to learn your squares and your cubes, at least the first 10. So now, let's look at how to apply this formula. Just like we did with the difference 2 squares formula where we had x squared and then later on that x represented the square root of it. Well, it's the same thing here. This is a difference, so I'm going to need the difference formula. Let me write it up here so we can see how that compares. Now, when I factor it, I'm going to get x minus y times x squared plus xy plus y squared. Okay, I have x cubes, I have x's, I have x squares. Let's get a handle on what all these are in relationship to these numbers. If this x cubed is my perfect cube, what is the root of that? Well, the root of 8x cubed is 2x. The root of 27 is 3. That's just the plane. That's the x and the y in my formula. All right, if I also need to know an x squared, because my formula has an x squared, what would this root squared be? Well, that would be 4x squared, wouldn't it? What would this root squared be? That would be 9. And we know that our x cubed was what we started off with. That was 8x cubed, and the y cubed is 27. So now I have a value for all of these things in my formula. All you gotta do is plug it in. All right, what is the x term? That's 2x. Let me write a little more legibly. All right, what's your y term? That's 3. What is x squared? Well, it's 4x squared. All right, now this is xy, x times y. You're actually just going to go multiply these two things together. So 2x plus times 3 is 6x. Then the y squared is 27. Okay? And this is a factored form of a difference of two cubes. Okay? So the next video will cover factoring by grouping with 4 terms, and then we'll go into trinomials. And then I'm going to make a whole separate video where I just work like 10 random problems. So be ready for those. And we are going to conquer this factoring quadratics thing one way or the other. See y'all next time. Bye.